CS340. I'm Frank. This is Payman. It's fall 2020, and we're going to do more, better, faster, stronger linear classifiers today. Okay, so last time we talked about using basically linear regression models to do classification by changing the output space from real value to unique real values like +1, -1 for the classes, right? And we went through this kind of awesome derivation of SVMs, where we started with a linear model predicting +1 or -1, and we said, okay, we can fit such a model, and the prediction that will output is just the sign of the parameter vector times the input feature vector. So W's are parameters as always. And we said, okay, well, you know, we could just train the linear regression model with our regular old squared error. The issue is that this will not necessarily give rise to models with the best classification accuracy, because in particular, you will penalize being right too much a lot, and that will cause your decision boundary to be put in a weird place. So we said, okay, well, what we really want is the 0-1 classification error, where we don't get penalized. We get a penalty or a loss of 0 if we get the sign correct. In other words, this is +1 equals +1 or whatever, or -1 equals -1. And we get an error of 1 if we, misclassify the instance. The problem is that this particular loss is not convex. It's hard to minimize in terms of the parameter vector unless the optimal error is 0, i.e. the classes are linearly separable, and then you can run the perceptron algorithm. And there's no gradient anywhere. It's just nasty. It's a nasty loss function to deal with. So we said, okay, can we build a convex approximation to this 0-1 loss, right? And we said, okay, well, we can look at this thing where we construct a new loss function to replace this squared loss function. We construct a new loss function that looks like this curve right here. We said, okay, that does what we want it to. It doesn't penalize us when we're wrong, and it linearly penalizes us when we're right. The problem is that if you set this W equal to 0, then the overall loss would be 0, and that's just kind of dumb, which means that the minima, you already know what the minimum is, and you're not going to learn anything, right? So instead, we said, okay, well, what if we just move this over? We introduce some slack into the system, stick this 1 on there, right? Then we have the hinge loss, right? This is a convex upper bound on the number of classification errors. And if you sum over all of the instances, this loss, and add L2 regularization, squared or not, doesn't really matter. It's called a support vector machine. Okay, that's pretty cool. So when we did this, we said, okay, well, this SVM, this is just, if you're going to go off and use SVMs, or you're going to use some software package out there, right? The way we wrote them in this class is we said, okay, we're going to sum up this hinge loss over all possible, over all of our training data instances, right? Using +1, -1 for Y. And we have this regularization parameter for that penalizes model complexity as we have throughout. Some software packages actually use a regularization parameter C, which lives out here, right? Okay. And it's worth noting that if you just multiply through by 1/C on both sides here, then if you identify lambda equals 1/C, this is the same thing, but the meaning of the parameter and the meaning of regularization in some of the support vector machine literature changes, right? So if you let C go to 0, then all you have is a regularizer. So if C is small, you have lots of regularization. If C is large, you have less regularization. So yeah, you can think of C as how much to focus on the classification error. This is really just a warning if you go off and you start using regularized support vector machine software packages, that you have to think about how the regularization parameter is actually included. And another sort of really highly creative way of deriving something that's super important. If you recall, we said, okay, what's a good approximation to the maximum function over a set of values? Here, there are only two values. Do you remember? Yeah. Log sum x, right? So if we replace this basically with log of the x, e to the 0 and plus e to this term, right? This gives us the logistic loss, okay? Then x of 0 evaluates to 1. And if we sum over all of the examples, our loss that we want to minimize to learn parameters for our classification, our linear regression-based classification, our linear classifier, looks like this, where you just sum over all the instances, you take a log of 1 plus e to the minus yi times w transpose xi, okay? And you can think of this as basically just a smooth approximation to this hinge loss, okay? This loss function is called a logistic loss function, and the model that this corresponds to is called a logistic regression model, okay? This is, it's worth, well, I guess we highlighted this on the next slide. So this is, yeah, it's not degenerate. If you plug in 0, this term turns to 1, and you get log of 2 instead of 0, so you can actually minimize this thing and not get a trivial solution. It's convex function, it's differentiable, so you can actually learn this using gradient descent instead of some sort of specialized solver that you need to use for support vector machines. You can also add regularization on here as well of any kind that you want, right? And in, I think, 2.5 weeks or something like that, we will see that this model has a probabilistic interpretation. Thank God, this is where I get really happy and get very, very comfortable. But basically, you will even be able to see if you squint that this is the log likelihood under a model with a logistic sigmoid link function and a Bernoulli distribution. Anyway, so we'll get here. It gets fun. What does that logistic loss look like? Remember, if the true label is -1 and our prediction is W transpose xi, and the output is the sign, then we really want 0 penalty over here. We want some positive penalty over here, and we said, okay, if we put a little margin in, we have some penalty here, which encourages the weight vector to further separate the data. The logistic loss looks like this. It's very similar to the rest. It's not a bound anymore, but it's smooth and it approximates the 0-1 loss. It's roughly linear here because of the log x term, and it basically has an extra little bit of penalty here that goes forever, that tries to push things even further. The models, yeah, basically they don't penalize for being too right, and they penalize for being very wrong. So that's it. Now we've got, like, really honestly 3 of the main hugely valuable, hugely important machine learning models covered at this point, right? So we have random forests, which are really awesome. And now we have logistic regression and support vector machines, and they're used everywhere. They're super fast for training. They're super fast at test time. Basically, you can train them on huge data sets using stochastic gradient descent, in particular logistic regression. And prediction is very simple. You just take a dot product with your weight vector and the feature vector for the incoming instance, right? The weights are easy to understand. Wj is how much xij changes the prediction in what direction. Basically, it's just a linear model. So if it's positive and you increase that particular feature dimension, it's going to cause it to be more likely to be class 1, and if it's negative, it's going to be more likely to be class equal -1. Okay. these models often give very, very good test errors on just arbitrary problems, right? And they're amenable to use in either sort of low dimensional feature spaces or high dimensional feature spaces. So in low dimensional feature spaces, if you use radial basis functions and regularization, you can get very good performance. And if you have very high dimensional feature spaces and you do regularization, again, you can get very, very good performance out of these. And the decision boundaries that you get are smoother than the sort of axis aligned choppy things that you get from random forest. So that's turns out to be good in a lot of cases. So in this paper that we talked about from Fernandez Delgado et al. In 2014, like how many, do we really need hundreds of classifiers to solve real world classification problems? They looked at, a bunch of classifiers and a bunch of data sets. Random forests were the most likely to be the best classifier. The next best class of methods was support vector machines, particularly with L2 regularization and using radial basis functions. And in general, you might want to take a look at this link and related kinds of articles that establish that all of us are chomping at the bit to get to the neural networks and deep learning at the end of the course, because of course they're awesome and they solve everything. But in reality, actually, particularly in reality, still support vector machines, logistic regression, random forests are very, very, very widely used, particularly when you have not huge data, basically. Questions at this point? All right, great. Now, we're not going to go into the mathematical details of this, but it's worth pointing out that there is, particularly when we think about support vector machines, and very recently when we think about logistic regression models, a perspective on what they're learning. Everybody dead inside, yeah. What's going on? There's this maximum margin perspective that's worth knowing about, so that if you want to look up stuff and understand what's going on, you can think about it. So let's consider a linearly separable data set. So here we have noughts and crosses, or X's and O's, or whatever you want to call it. Have two features, and the two classes are obvious, the X's and the O's. So here is a line or a hyperplane with W transpose X equals 0. Okay. So just to be clear, I don't think we've actually really explicitly done this, right? So if our vector W is here, what we're really saying is, okay, when we're talking about this, we're using the dot product to project these vectors onto this vector. The offset comes from the additional dimension of W, so that moves it away from the origin, right? And because of the offset, when W transpose X is, or the intercept term, I guess, when W transpose X is greater than 0, we're over here on this side of the projection, and when W transpose X is less than 0, we're on this side of the projection, right? And this is when we classify one versus the other, whatever, okay? Cool. So we talked about the perceptron algorithm. We gave the algorithm, you add a little bit of each data point, to the weight vector, and we said, okay, if the data points are linearly separable, then the perceptron algorithm will find some classifier with 0 error. So it might find this one, it might find this one, it might find this one. The question is, are all 0 error classifiers equally good? Payman?
No.
Well, up to now, they are, right? We have no way of,
yeah, up to now, yeah, but when you...
Exactly, so I'm being a little bit of a jerk, but yeah, so yes. So up to now, no, but intuitively, we probably would think that one's a better regressor, right? Because, what if the distribution of the O's looks like this and the X's actually looks like this? If you give yourself as much slack or margin, as it were, right? If you give yourself as much margin as possible, then the chances are that when you get test data, you
didn't we say red is the best before because it has the one that has the lowest slope? The best one.
Yeah. So here we're not doing regression, right? So we're not doing regression. So that, yes, when we were talking about regression, we wanted we provided some intuition that, that was to provide intuition that models with a small number, with small parameter values tend to generalize better. Yeah. So here we're saying, okay, there are some parameters and we're still going to regularize and so on and so forth. But even when we do regularization and even when we want to have a W that actually maximizes this margin, right? We want it to be as far away from the training instance as possible. So that's exactly what a maximum margin classifier is. It chooses the classification parameters that make the hyperplane as far away from the classes as possible. So, this red line is a perfect classifier with a small margin, right? These examples are really, really, really close. So the margin, basically the actual distance from the data point to this line there, that's really small. The perfect classifier with a maximum margin looks like this, and the margin is basically the distance to the closest examples. Okay. So why should we maximize the margin, or why should we care about methods that maximize the margin? It's what I've already said. If the test data is close to the training data, then the max margin leaves more room before we make an error. Okay.
Wouldn't this make the regression line more sensitive to changes like error data?
This is not a regression line. Right. So we're plotting something very, very different, right? So yeah. Yeah, so let's be very, very, very clear. I think this is the way to do it, right? When we're talking about regression, this is the output, right? Right. If we were going to think about this as let me get one without much crap on it. If we were thinking about this as a regression, actually the same kind of intuition applies. So let's say these are labeled +1. So these would all be, if we plotted y on here, this would be yi, right? Okay. These are all sitting up on the plane at +1, right? And these are actually all at -1. These are at +1, +1, +1, something like that, okay? So the regression line, if it were, I mean, there's no regression line. There's a plane that comes through here like so, right? And crosses the plane at a line. So this intersection that we're looking at is at a particular line, right? So the regression surface is out of the page, right? Cool. Yeah, and that, yeah. So we're not we in W space, we still want this to be the lowest slope plane. We want it to be the slope, the slope that the plane that changes with respect to the inputs as slowly as possible, and that's what regularization will give you, right? But what we're talking about here is the orientation of this surface, right? That's what we're talking about, and that the orientation of the surface is going to be controlled by the loss, right? Everyone has regression burned into their minds right now. Yes, that's probably true. Have fun with the midterm. I hope you're enjoying it. I guess this correctly gives smaller values on either side of the line. We've got our stuff that's questionable in the gap data. Yes, that's true. Would it be possible to do something to push the distribution of distance of border points to the line to be as uniform as possible using some measure of entropy? I mean, the max margin techniques that we're talking about actually do this. Is the margin basically the Euclidean distance? Yeah, it is the Euclidean distance. That is correct. And although you can use whatever metric you want, but Euclidean distance is usually the distance that is used, and it is the minimum value. So the absolute minimum value that you could use here to describe this. Ooh, that's a good question. I shouldn't have said that because now I have to think about it. I'm not going to think about it. 2 or 3. Should be 2. Are the points that have the closest points on either side of the line, and yeah, basically max margin says that they will have the same length, right? So that's going to happen automatically. Anyway, these are wonderful questions, but these are tan slides, first of all. Second of all, to actually technically answer these questions is pretty involved because we haven't introduced slack variables, we haven't introduced Lagrangians, we haven't done any of the stuff that we normally would do to introduce support vector machines in the sort of the maximum from the max margin perspective. Like if the objective is to find these points and minimize and maximize this margin, then it's a different kind of a derivation. The point is that if your regularization is small enough, but still non-zero, support vector machines find the maximum margin classifier. Okay, you can look that up in the literature. There's, you can see proofs for this. The condition is that the lambda needs to be small enough that the hinge loss is exactly 0 in the solution. In other words, you can't regularize so much that you actually introduce errors. And the origin of the name for support vector machines are the support vectors are the points that are closest to the separating hyperplane. Okay, and you can look at the bonus slides for a little more information about that. And a very, very recent research result, I think it's probably 2 years ago now, maybe 1.5 years, something like that, and that's very surprising, is that logistic regression also finds a maximum margin classifier. So support vector machines were derived originally from this perspective. Logistic regression originally comes from a probabilistic perspective, and it turns out that both methods actually arrive at max margin classifiers, which makes them good. That's kind of the reason why they're good. However, in the logistic regression case, the proof and the result is a very strange one, which is to say that in logistic regression, you will only find the max margin if you have no regularization, and more to the point, you can only fit it using gradient descent, and that's a really, really, really weird result. But it's recent and cool. How do we determine the number of points closest to the line to consider as a hyperparameter? No. So what, it would be fun someday when we meet again in another more advanced class and I derive support vector machines from the max margin perspective. It would be fun to show how that they arrive. But basically, you can define this line in terms of the closest points. The number of closest points arises from trying to maximize the margin. Basically, it just pops out. They're the ones that are closest within some. That's all I'm going to say here. It gets very hairy and very technical very quickly. It's not a hyperparameter. For our purposes, what we're really trying to communicate here is support vector machines are linear regression models with a different loss function, the hinge loss, right, and regularization. Okay? And when you use some software package, which you won't have to implement as support vector machines, except maybe in the final, when you use some software package, you're going to get a solution that looks like that maximizes the margin, which is why these techniques are good. That's what we communicate in this class. Phew. Okay, good questions. Enough questions here that I'm going to keep going on. Okay, so we had this previous example of identifying important emails. Surely all of you remember this. Important is +1 and not important is -1. We can solve this using binary classification by taking the scientific linear model as usual. And we have these, we've been talking about convex loss functions, hinge or logistic. They allow us to find an appropriate W. The question is, what if we want a probabilistic classifier? And this is, again, we're getting closer and closer to things that I'm really, that I spend my time doing. Right? What if we want a probabilistic classifier? Again, this is 440, 540 kind of material, but we'll touch on it in a couple of places now and in like 2 weeks. If we want a model of what, of the probability of yi being important. So what's the probability that yi equals +1? And of course, the probability that yi equals -1 given xi is just 1 minus that, right? What if we want this for use in the decision theory kinds of situations that we talked about before, where we want to, decide whether to label something as important or not, and have a cost associated with making a mistake. So what are we doing? So if we just temporarily use zi to indicate w transpose xi, so this is what we're looking at. This is our, this is, yeah, it is what it is, right? So zi is the value of w transpose xi, and we're going to vary xi effectively, right? Then our prediction, y hat I, is just the sign function. So, it returns +1, -1 here, and, nothing in between at the measure 0 spot. Prediction sign maps w transpose xi, or here plotted as zi, to the elements, solely the elements -1, +1. We know this. If it's positive, we predict 1, negative, we predict -1. For probabilities, we want to map w transpose xi to the range 0 to 1. We don't want to go down here. We want it to be 0 to 1. Okay. If xi is super positive, we want the output to be close to 1. If it's very negative, we want it to be close to 0, right? And if it's close to 0, we kind of want it to be, 50-50. Okay. So this is, again, we're thinking about how to write down an expression. So we're given w transpose xi from some model. We have some w transpose. We learn it with support vector machines or logistic regression or whatever, right? So we have this model. So we want to know, we're looking at estimating one probability, +1, okay? And I see, a suggestion, sigmoid, 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 that's right. So we want a transformation that looks like this. And the most common choice is the sigmoid function. So we're going to call h the sigmoid function here. It's just 1/1 plus e to the minus zi, where zi, again, is, you can think of this as w transpose xi. This is the range, the domain of the logistic sigmoid. The values of the sigmoid function, if you're unfamiliar with the sigmoid function, match what we want. At h of 0, or h of zi equals 0 is 0.5. H of negative infinity way out here is 0. Way over here it's 1. And for values in between, it does what you would expect. It looks like this plot right here.
Would this work if we weren't doing binary classification?
So the sigmoid returns a probability, or a number between 0 and 1, which we will interpret as a probability. So that's will become relevant even later in this lecture when we talk about multi-class classification. But the short answer is no, it only applies to binary classification. If our n classes do binary classification n times, I don't know, though that seems inefficient. I see, so that's a comment on that. That's actually pretty much what you have to do, and we'll get to that in just a little bit. So using the sigmoid function, we can output probabilities for linear models, right? So wherever you get the W from is going to be slightly different from logistic regression. It's going to be slightly different from support vector machines. It's going to be slightly different if you just use the L2 loss, right? Or perceptron or whatever. We can output probabilities or numbers that we interpret as probabilities using the logistic sigmoid. you can derive the probability of the other class by using, the laws of probability, and a little bit of algebra, which is too annoying to stick on a slide, which basically says that the opposite probability just changes the sign here. And if you look a little bit at that, you can see that the same thing is in play here. Like the likelihood of this observation, the likelihood is just stick the yi back in here. So if you think about in advance of what's going to happen like 2 weeks from now, when we talk about probabilistic interpretations of logistic regression, we're going to have a sigmoid link function that outputs probabilities for Bernoulli likelihood, and Bob's your uncle. That's the probabilistic interpretation of logistic regression, and it's awesome. But for now, we're saying you can get these weight vectors from anything, and we can transform them into probabilities, and we can use those for decision theory. So, and indeed, this will seem totally magic, and it is. It's just, well, we're just like pulling stuff out of our collective butts. But again, this does correspond to maximum likelihood estimation, or minimizing logistic loss corresponds to doing maximum likelihood estimation in a model with this as a link function. Questions? Okay. Type now or forever hold your fingers. No. So we have to have like whole new like idiomatic expressions for COVID. Type now or forever hold your fingers. That's a good one. Somebody tweet that out. Credit me. Okay. So now we've done linear. So wow, this is awesome. We're cooking with gas in this class now. So we've got random forest, logistic regression, support vector machines. We know classification. We know regression. We know clustering. What else do we know? Know a lot of stuff. We're still going to do classification, but now we want to think about like multi-class linear classification. Okay, seems like a reasonable thing to do. Don't do this on your midterm examination. But what we've been doing is we take our feature matrix and we have our labels, +1, -1. Is there a cat in the image or not, right? What if we want to or need to do multi-class classification? So, we've got one, that's a cat. This is a dog. This is a carrot. This is a porpoise. Whatever, okay? We've got lots of classes. So we can classify an image as a cat or a dog or a person. This is easy to do with decision trees or naive Bayes or k-nearest neighbors. Like it's straightforward. If your feature vector lands in the zoo of labeled feature vectors and your k-nearest neighbors are all dogs, you're probably a dog, or this image is probably a dog. I don't mean to say that anybody in the course is a dog. For linear models, we have to do something slightly differently. We need a little bit more of new notation, right? So suppose, in fact, like the comments already say, but you can't see those comments, but the comments suggest that you can just do binary classification in time. Suppose that you only know how to do binary classification. And of course, what we'll say is that one versus all. So basically, if you learn a bunch of classifiers that classify each particular object class relative to everything else, one versus all is a way to turn your ability to do binary classification into a mechanism that does multi-class. Okay? So the easiest and not optimal, because we're going to talk about some more important things to do in just a little bit. During the training phase, for each class, you just train a classifier for that particular class. You have a cat detector, a dog detector, or a cat classifier, a dog classifier, a human classifier versus everything else. So we have K classes. This gives us K classifiers. So the prediction phase, we take those binary classifiers and we get a score for each class C. So here's an image. We extract some features, xi. We run our cat classifier, dog classifier, which of course would be a detector. Is it there or not? So on and so forth. Human detector. And you get some sort of a score. Okay, now I haven't said what the scores are, but let's just assume that you get some sort of score, and whichever the score is maximum, you predict that. You predict the class with the highest score. So if we want to do one versus all logistic regression for classifying, between a bunch of different classes, for instance, we train a separate classifier for each class. Every classifier tries to predict the correct class as we just described. But what we have is we get a weight vector for every single class. And using that weight vector, when dotted with the vector, the feature vector for a particular instance, tries to predict +1 for class C and -1 for all others. So we can pack those all up in a matrix W, which has k different weight vectors, and all of those weight vectors are d-dimensional, where d is the number of features. So the point is we have k way classification, right? Each row gives weights for a binary logistic regression model to predict class C, okay? Cool. What does this look like? For each class C, we compute WC transpose XI. So basically we go through all the rows and we compute, after extracting features or whatever, getting our features for whatever our application is, and we compute a score, okay? So ideally what we'd get is that the sign of these predictions would be positive for only one class and -1 for all of the others. Okay? In practice, it might actually be +1 for multiple classes or no class. What we do to predict a class is we take the maximum value of W transpose Xi, the highest score, right? Over here, obviously, if we're doing, what is in this picture, the human has the highest score. It's higher than -0.8 and -0.1. Okay, so easy, right? Cool. If we do multi-class classification using one versus all in the manner we've just talked about, you should think about what the shape of the decision boundaries looks like, and it's kind of cool. So we know that a binary linear classifier splits using a hyperplane, projecting all the data points onto your parameter vector, and then that defines a hyperplane where it's equal to 0 and blah, blah, blah. These are all class 1, these are all class 2, or whatever. Divides space into two half spaces. But what we just said is, for each class, we're looking at the relationship between the score for that class and the other classes. So if you do a multi-class linear classifier, it's basically an intersection of half spaces, just like it was in k-means, right? So it divides the space into convex region. And this blue region is a region where we have, W transpose Xi is greater than W transpose Xi for the green class. Blue is greater than the magenta class, blue is greater than the red class, blue is greater than the black class, and so on and so forth, okay? And everything in here would be classified as blue because the output from that model is greater than all of the other models in that region of space, okay? And since all of them can only be less than or greater than or equal to relations, then we know each one of those defines a half space. Okay. As a little digression, what we're talking about when we're doing multi-class is different than multi-label classification. Okay. So you can have multi-label classification problems as well. Don't do this for midterm either, please. Where you have your data matrix and actually you have multiple labels. Sounds familiar, right? You have multiple labels for your input feature matrix, right? So basically there can be more than one correct class label. You could arrive at this situation when you're doing linear regression, when you're doing regression rather than classification. Here we could also fit k binary classifiers, but we would take the sign of each one of them as an independent label. Right? So you can have multiple objects, for instance, in an image, and each one of them would trigger, and that would be fine. But if we go back to multi-class classification where we have one correct label, right? We train the clay classifiers, we predict by maximizing overall classes. So we maximize this expression with respect to C, right? That's how we do our prediction. We're going to use some notation here, and this is important. WYI is the classifier where the class basically the weight vector is the true, is the weight vector corresponding to the true class. It's the row of this corresponding to the true class label. So y equals 2, then wy equals w2, okay? So although you can, and lots of people do multi-class classification the way we just described, there is a little bit of a problem, and it takes a little bit of head scratching to recognize it. So hopefully I can get it across to you. The problem is that we didn't train our parameters WC so that the largest amongst the alternatives is WYI transpose XI, so that YI, the true class label, maximizes over all of the alternatives, right? We just said, ooh, like the value, what we didn't do is we didn't say the score of the true class has to be greater than the score of all the other classes. So it could be, you know, exactly like this, right? So here we have this horrid dogman picture, right? Okay. Where it's not really any of them, right? And they're all going to get negative scores, so there's no winner, right? So what do we have to do? We have to choose the biggest one. That's what we said, right? So we're going to choose the biggest one, right? Great. But what we would really like is we'd like to have it so that when we train, this ends up being even more positive relative to its neighbor. So. Okay, yeah, okay. I think I just guffed that up pretty good in terms of an explanation. So video edit back 2 minutes, okay? So we're going to predict dog here, right? But let's assume that we want this to be human. This one always screws me up. I didn't screw me up last time though, so whatever. Great. So what we want is we want to elevate this so that it's not very human, but maybe we want it to be human, and we want to elevate this because that's the true label, okay? We really should just put the true label on here so that I don't screw that up, okay? So the point is, and this will be hopefully clear when we talk about it with support vector machines, is that the scores that we get out of the different classifiers aren't normalized relative to one another, right? So you might be super negative all the time for one, or super positive for another, or the ranges are such that one of the classes will dominate all the others totally inappropriately, okay? The point is that we want to make the outputs of the individual classifiers scores, the scores actually positive or negative relative to one another, okay? And the multi-class hinge losses and multi-class logistic losses do this, okay? So can we define such a loss that does this, okay? Such that when we maximize over C in particular, we choose the correct label YI. So let's think about the derivation we made for the hinge loss, okay? So first thing we said, okay, well, we want this to have the same sign as YI, right? Which means we want a negative when Y is negative and positive when Y is positive. So we can just multiply them together, and we want this whole product to be greater than 0 to classify. If that's true, then we classify all of our instances correctly. We said, okay, if we construct a loss with constraint violation as the thing, then if we set W equal to 0, then we can we get a degenerate loss. We don't learn anything, so we avoid the non-degeneracy by putting this margin or slack in here, right? And then we said, okay, the amount by which we violate this constraint is our loss, and this was, you know, this is this loss like so, right? We can derive multi-class support vector machines using the same steps. So the idea is that we want the score. We want this score to be greater than all alternative classes for all classes that are not the correct class. Okay, so we're not in +1 -1 land here. Remember, we're in, like, you know, k different classes land, right? So we really want the scores to be properly calibrated with respect to each other, okay? So if we directly penalize a violation of this constraint, it's degenerate, but let's say that we actually really want, the score of the correct class to be greater than, any alternative class plus some margin, okay, for all classes other than the correct class. Okay. Or equivalently, we can write down the constraint that we want, which is given by this expression right here. Now we have to think about this just a little bit. So what do we really want? We really want a statement like this, and this is now the multi-class SVM loss, okay? What we really want is, for instance, a sum loss, okay? So we're saying we want to, for any particular data set, so we're gonna eventually sum this over I for all the data, right? For every individual data point, we want to sum over all the classes not equal to yi, right? The constraint, right? So we want to make this thing bigger than this thing. Okay, so we know yi, so we've got yi from here, right? And then we want to ensure that for all other classes, the score of those classes is lower. That make sense, Payne?
Class individually or the sum?
Sum, right here. So we're going to sum. So we want them to be individually lower, right? And we want all of them to be individually lower. So we will penalize the sum, right? Alternatively, we could do something like this, which is also pretty cool. We say, okay, we're going to, again, still sum over y, but we can look for the maximum over all of the classes not equal to y of the largest constraint violation. Okay. You can sort of, if you think about it, these two are going to work out to kind of doing the same thing, right? Because if you try to push down the maximum constraint violation, then all the constraint violation, once you push that one down, then some other one is going to be the maximum, and then you push that one down, and so on and so forth, right? And that's kind of the same thing. It's just looking at the sum, right? So that's what a multi-class SVM is basically. So for each training example, the sum rule penalizes for each C, or I guess for all C's that violate the constraint, and the max rule penalizes for the one C that violates the constraint the most. So the sum gives a penalty of k minus 1 for w equals 0. Max gives a penalty of 1. That's fine.
Do we sum over all y for the actual loss function, or where did you add that?
Yeah, so for the overall loss function, when we're training the support vector machine, obviously we sum over all I in both of these cases. Okay, so we're talking about individual examples, right? And yeah. So if we add L2 regularization to this, right? So this would be sum over WK, K2, remember? So now we have a bunch of different linear classifier weights, right? If we sum over if we regularize this as well, L2 regularization, both of these are multi-class support vector machines. The max rule is more popular. The sum rule usually works better, and both are convex upper bounds on the 0-1 loss. So, but the main point here is that the loss function, which we're not talking about how to optimize, but these losses here explicitly encourage compatibility between the scores between the k different classifiers, trying to push the true score larger than all the others for all 1 out of k classification instances. Yeah. Okay, cool. We've done some stuff. We're getting some stuff. We're like, we're getting into this is like the really speedy part of the class where you really have to go off and learn a bunch of stuff on your own. It's fun. So we have touched some pretty important stuff today. So the logistic loss is a smooth convex approximation to the 0-1 loss, and it gives rise to logistic regression. And then that really will start to solidify the idea that regression and classification are exactly the same thing. They just have different loss functions which correspond to different likelihoods and so on and so forth. Support vector machines and logistic regression are super widely used, and they're very, very powerful. In addition to random forests, you can do quite well in the real world making money doing, let's find some good features and use L2 regularized logistic regression or support vector machines for classification, whatever. We highlighted the idea that both of these methods, logistic regression and support vector machines, can be thought of as max margin techniques, and that's a lot of where they get their strength from. But they both are just linear classifiers, which divide space into two half spaces. You get slightly different parameters, vectors for both of them. We introduced a sigmoid function. If you're unfamiliar with it, get familiar with it as a way to turn linear predictions into probabilities. Saying basically you can turn the logistic regression or a support vector machine weighted predictions into probabilities. We talked about how to do multi-class classification via one versus all construction, and then we said actually we can learn better parameters for one versus all classifiers by constructing loss functions that explicitly encourage compatibility of scores. Okay, cool. That's it. Let's see. Class today was confusing. Sorry, Dominic. I can imagine that. Emily, I apologize as well. Yes, like usual, it will get better when you do the assignments for sure. But I'm here for you, both to confuse you and to try to make it a little bit better. So Dominic or Emily, would you like to ask any questions in the time remaining? Yeah, I mean, Dominic's comment, we just need to work through the related material and it'll come together. That is without any question true. The fundamental concepts are pretty straightforward, right? You have a linear model, you have to change the loss function to something. The loss function, we've talked about a bunch of them. And then the one versus K thing is totally fine. It will also come together when we start talking about multi-class logistic regression, where it becomes a lot clearer and cleaner to talk about these things. That'll come in a couple of weeks. I recognize that it would be very nice to have some what, how do you say it, like the prompters that politicians use, where you can like actually look at the camera while you're doing your thing. It's kind of annoying that I'm always looking over here or whatever. Yeah, it would be more professional to be able to look right at you, but I can't, unfortunately. Lots of startup ideas, yeah. All right, well, if that's it, that's it. Good luck on your midterm. Ming, I agree. Me too. I need more brain cells. We all do. But the best part about this kind of thing is you're not bored, and running from boredom is it's the story of most of our lives. All right. Thank you all. Thanks, Payman.
Thank you. Have a nice weekend.
Yeah, you too.